So today we'll solve one example related to multi-degree of freedom system. As you can see in the question, we have this example: find the natural frequency and mode shapes of the 3-degree of freedom system as shown in the figure. Okay, for this situation where m1, m2, m3 equal to m is equal to 10 kg and k1, k2, k3 is equal to k equal to 200 Newton per meter. Now this is our system. As you can see, it is a 3-degree of freedom system because we have 3 displacements x1, x2 and x3. Now the differential equation of motion we can write the differential equation of motion for the system can be expressed as okay, m1 x1 double dot plus k1 x1 plus k2 x1 minus x2 is equal to 0. Okay, then m2 x2 double dot minus k2 x1 minus x2 plus k3 x2 minus x3 is equal to 0, and m3 x3 double dot minus of k3 into x2 minus x3 is equal to 0. Let us say it is our first set of equation. Now this equation 1 you can write here. Equation 1 may be expressed as m1 x1 double dot plus k1 plus k2 into x1 minus k2 x2 is equal to 0, then m2 x2 double dot minus k2 x1 plus k2 plus k3 x2 minus k3 x3 is equal to 0. Okay, then we have m3 x3 double dot minus k3 x2 plus k3 x3 is equal to 0. Let us say this is equation 2. Okay, now in matrix form, write equation 2 in matrix form can be expressed as m1 0 0 0 m2 0 0 0 m3. Okay, this is our mass matrix, multiply by x1 double dot x2 double dot x3 double dot plus the stiffness matrix, that is your k1 plus k2 minus k2 0 minus k2 plus k3 minus k3 0 minus k3 this is the stiffness matrix. Then we have x1 x2 x3 column matrix is equal to 0 0 0. Okay. Let us say this is equation 3. Okay. Now you can write, now substituting the boundary conditions, we have m1 is equal to m2 is equal to m3 is equal to m, and k1 equal to k2 equal to k3 is equal to k. So we'll have the equation as m0 0 0 m0 0 0 m, okay, m. x1 double dot, x2 double dot, x3 double dot plus 2k minus k 0 minus k 2k minus k 0 minus k k x1 x2 x3 is equal to 0 0 0. Let us say equation 4. Okay. So we can write that the dynamic matrix C, as we know, it is equal to the inverse of the mass matrix multiplied by the stiffness matrix. Okay. So now this inverse of the mass matrix can be obtained from this relation m divided by its determinant. Okay. Now determinant of this mass matrix M is equal to MQ, obvious. Okay. And adjacent of M will be m square 0 0 0 m square 0 0 0 m square. Okay. So the inverse matrix of mass will be 1 by m 0 0 0 1 by m 0 0 0 1 by m. And the dynamic matrix C will be 1 by m 0 0 0 1 by m 0 0 0 1 by m into 2k minus k 0 minus k 2k minus k 0 minus k k, okay, and that is equal to, we can write 2 2k by m minus k by m 0 minus k by m 2k by m minus k by m 0 minus k by m k by m. Okay. Now the matrix equation is given by I x double dot plus c into x is equal to 0. So the frequency is given by lambda I minus c into lambda is equal to 0. So we can express this as lambda 0 0 0 lambda 0 0 0 lambda minus two k by m minus k by m 0 minus k by m 2k by m minus k by m 0 minus k by m k by m into lambda 1 lambda 2 lambda 3. Sorry, this x1 x2 x3, huh? This will be x, huh? This is equal to 0. So we'll have lambda minus 2k by m, okay, k by m 0, then k by m lambda minus 2k by m k by m 0 k by m lambda minus k by m is equal to 0. So we can write here as lambda minus 2k by m into lambda minus 2k by m into lambda minus k by m minus k square m square minus k by m into k by m into lambda minus k by m is is equal to 0. So if we further solve it, we will have lambda minus 2k by m into lambda square minus lambda k by m minus lambda square 2k by m plus 2k square by m square minus k square by m square minus k by m into lambda k by m minus k square by m square is equal to 0. Okay. Or we can write this equation as lambda by 2k by m into lambda square minus lambda 3k by m plus k square by m square minus lambda k square by m square plus kq by mq is equal to 0. Upon further simplification, we will have lambda q minus lambda square 3k by m plus lambda k square by m square minus lambda square 2k by m plus lambda 6k square by m square minus 2kq by mq, okay, minus lambda k square by m square plus kq by mq is equal to 0. So lambda q minus lambda square 5k by m plus 6 lambda k square by m square minus kq by mq equal to 0, because we have this and this get cancel out. Okay. So upon further simplification, we can write this as lambda q minus 5 lambda square of k by m plus 6 lambda k square by m square minus kq by mq is equal to 0. Now substituting the value of k and m, we have lambda q minus 5 lambda square into 200 by 10 plus 6 lambda 200 square by 10 square minus of 200 q by 10 q is equal to 0, or we can write this as lambda q minus 100 lambda square plus 2400 lambda minus 8000 is equal to 0. So the roots will be, you can find out as lambda 3 will be 64.939, lambda 2 will be 31.099, lambda 1 will be 3.961. Corresponding frequencies, natural frequencies will be omega 1 will be 1.99 radian per second, omega 2 will be 5.57 radian per second, omega 3 will be 8.05 radian per second. Now this is one answer, we got the natural frequencies. Now next is mode shapes. How to find mode shapes in the example? So we have the equation lambda I minus c into x is equal to 0. We have this. So we will use 3.961 0 0 0 3.961 for the first lambda 1 value 0, then 0 0 3.961 minus the C matrix. Okay, by substituting the values we will have 40 minus 20 0, then minus 20 40 minus 20 0 minus 20 20 into x1 x2 x3, right? This is equal to 0. If you solve this, we'll have minus 36.039, then 20, then 0, then we have 20 minus 36.03, then 20, then 0, 20 minus 16.03, okay, into x1 x2 x3 is equal to 0. So we will have the equations as minus 36.039 x1 plus 20 x2 is equal to 0, and 20 x1 minus 36.03 x2, okay, plus 20 x3 is equal to 0. Let's say this is 1, this is equation 2, and further we'll have 20 x2 minus 16.03 x3 is equal to 0. Let's say this is equation 3. So from equation 1 we have x2, okay, x2 will be equal to 1.8015 x1, okay, and from equation 2 will have 20 x3 will be equal to 20 x1 minus 64.9 x1, that is minus 44.908 x1, okay. Now the first mode shape is given by is x1 x2 x3 is given by 1 1.8015 minus 44.908. This is the first mode cell. Now coming to the second mode cell. Second mode shape, by substituting the value of lambda, that is 31.099 in the equation lambda I minus c into x equal to 0, will have 31.099 0 0 0 31.099 0 0 0 31.099 minus 40 minus 20 0 minus 20 40 minus 20 0 minus 20 20 whole into, you can say this whole into x1 x2 x3, okay, is equal to 0. So if you solve this, we'll have minus 8.901 20 0, then 20 minus 8.901, then 20, then 0, then 20, 11.099, okay, then x1 x2 x3 is equal to 0. Minus 8.901 x1 plus 20 x2 is equal to 0, and 20 x1 minus 8.901 x2 plus 20 x3 is equal to 0, then 20 x2 plus 11.099 x3 is equal to 0. So from the above equations we have x2 0.445, x3 is equal to 0.445 x1, and x3 is equal to minus 16.03 x1. So the second mode shapes is x1 x2 x3 is equal to 1 0.445 minus 16.03, okay. So this is the second mode shape. Now coming to the third mode. So substituting lambda 3, that is 64.939 in the equation in the equation lambda I minus c into x is equal to 0. So we will have 64.939000 64.939000 64.939 minus 40 minus 20 0 minus 20 40 minus 20 0 minus 20 20 whole into x1 x2 x3, okay, that is equal to 0. So we'll have the value as if you solve this, we'll have 24.939 20 0, then 20 24.939 20 0 20 44.939, okay. This multiply by x1 x2 x3, this equal to 0. Now 24.939 x1 plus 20 x2 is equal to 0. 20 x1 plus 24.939 x2 plus 20 x3 is equal to 0, and the third equation will be 20 x2 plus 44.939 x3 is equal to 0. So from this set of equation we can have x2 as minus 1.246 x1 and x3 will be 11.07 x1. So the third mode shape can be expressed as the third mode shape that is your x1 x2 x3 will be 1 minus 1.246 11.07. So we got the 3 natural frequencies and the 3 mode shape. So in this way we can solve problems related to the multi-degree of freedom system, okay. So now we will continue with this Rayleigh method, okay, Rayleigh method. Now this so if you consider a single degree of freedom system, let's say we have a rigid support here and we have a spring with stiffness k, suppose a mass extended at the end, let's say mass is m, stiffness is k, displacement is x, okay. Now a system is said to be conservative. We can write a system is said to be conservative if if you can say no energy is lost due to friction, or we can say energy dissipating non-elastic members. Okay. And the total energy of the system remains constant. The energy of a vibrating system is partly potential and partly kinetic, you can say kinetic. Sum of these two energies remain constant. The kinetic energy T is stored in the mass by virtue of its velocity and potential elastic deformation. So you can say principle of conservation of energy can be expressed as T plus U is equal to constant, okay, or you can say d by dt of T plus U is 0. Let's say equation 1. Okay. Now the kinetic and potential energies are given by let's say the kinetic energy is given by half of m x dot square. Let's say equation 2. The potential energy U will be half of k x square, equation 3. Okay. Now substituting the values of T and U in equation 1, mx double dot plus kx is equal to 0. Equation 4. The principle of conservation of energy in the context of undamped vibration system may be restated as T1 plus U1 is equal to T2 plus U2. Let us say equation 5. Okay. For two different instances, let us say this is for instant 1, this is for instant 2. Okay. Particularly, you can say this subscript 1 is used to denote the time when mass is passing through the static equilibrium condition position, we can say position, that is E1 equal to 0. So if we refer subscript 2 as the time corresponding to maximum displacement of mass, we have the kinetic energy T2 will be 0. So equation 5 becomes T1 plus 0 is equal to 0 plus U2. Let us say this is equation 6, or we can say that T max is equal to the U max. Okay, maximum kinetic energy is equal to the maximum potential energy. Let us say this is equation 7. Now this equation 7 indicates the Rayleighs energy method which gives the natural frequency of the system. Natural frequency of the system. Okay. Now this Rayleighs principle, okay, Rayleighs principle is used to find the approximate value of fundamental natural frequency of a discrete system, not a continuous system, discrete system. Okay, the kinetic energy and potential energy of a n degree of freedom, we can say in a generalized manner, of a n degree of freedom discrete system can be expressed as, let's say, for t can be expressed as half of m into x dot, okay, and this v is half of k into x for discrete system. Now to find out the natural frequency, assuming a harmonic motion of this x equal to capital X cos omega t, where this x indicates a vector of amplitude, and omega is the natural frequency of vibration, Okay. Now if the system is conservative, maximum kinetic energy is equal to maximum potential energy as per Rayleighs principle. Okay, so you can say P max is equal to V max. Some books prefer U, some prefer V, so the notation doesn't matter. Okay, so we can say that T max is equal to half of m into x in vectorial representation into omega square, and V max will be half of k into x. Okay, by equating T max and V max, T max and V max, we have omega square will be k into x divided by m into x. Okay, So the right hand side of the equation is known as Rayleighs quotient. Okay, this part is known as Rayleighs quotient and is denoted by R of x. Okay. So this is all about your Rayleighs principle. Now using this Rayleighs principle, if we solve the same example that we have solved, okay, this spring mass system is there, we have this mass, okay, m1, m2, m3, we have k1, k2, k3, okay. Let's say x1t, x2t, time bound displacement, okay, x3t. The same boundary conditions, m1 is equal to m2 is equal to m, relation is equal to m, and k1 is equal to k2 is equal to k3 is equal to k. Now the equation of motion, of the system can be expressed as m1 x1 double dot plus k1 x1 plus k2 x1 minus x2 is equal to 0, and m2 x2 double dot minus of k2 x1 minus x2 plus k3 into x2 minus x3 is equal to 0. Okay. m3 x3 double dot minus k3 into x2 minus x3 is equal to 0. So in a more simplified manner we can say it is m1 x1 double dot plus k1 plus k2 into x1 minus k2 x2 is equal to 0, m2 x2 double dot minus k2 x1 plus k2 plus k3 into x2 minus k3 x3 equal to 0, and m3 x3 double dot minus k3 x2 plus k3 x3 is equal to 0. So the mass matrix is m into 1 0 0 0 1 0 0 0 1. Okay, the stiffness matrix K, okay, stiffness matrix K is equal to, let's say it is 2 minus 1 0 minus 1 2 minus 1 0 minus 1 1. Okay. So now substituting the mode shape and expressing the mode shape and expressing the Rayleighs quotient as R x vector is equal to omega square, that is k x divided by m x is equal to k into 2 minus 1 0 minus 1 2 minus 1 0 minus 1 1 okay 1 2 3 m 1 0 0 0 1 0 0 0 1 into 1 2 3. So it is 0.2143 k by m. Okay. So we can say the natural frequency omega 1 can be represented as 0.4629 root of k by m. So in this way, using Rayleigh's principle, we can find out the natural frequency also. Okay. Now the last part of this lecture is Rayleigh-Rees method. Okay. So this method, you can say this method is an extension of Rayleigh's method, we can say. Okay, it is based on the premise that a closer approximation, we can say, approximation to the exact natural modes can be obtained by superposing a number of assumed functions then by using single assumed function as in case of Rayleigh's method. This is the basic difference. Okay. So in the next class we will be continuing. Thank you.